my name is Sydney Meyer, and I am in section W03 of Physics 2211. This is my lab report for Lab 2, the motion of a falling object. The goal of this lab is for us to learn more about the forces that act on a falling object. To completely analyze an object moving, we create a computer model to predict the motion based on Newton's second law, gravity, and drag force. We do this so that we can better understand these forces and how they affect objects in everyday motion. From understanding Newton's second law, we are able to understand more about the kinetics of everyday motion. The law states that the rate of change of momentum is directly proportional to the sum of all forces acting on the object, which then can be related to velocity, as the change in velocity is equal to the net force divided by mass times the change in time. The gravitational force is the attractive force that exists between all objects with mass or energy. It points towards the Earth's center of mass and can be calculated by multiplying the mass of an object by the acceleration due to gravity, 9.8. Lastly, the drag force is a force that opposes the motion of an object through a fluid or air. It is calculated by squaring the velocity and multiplying it by a coefficient v that depends on the environmental conditions. Lastly, we have a sum of force statement for the two models we are going to make that predict the falling motion of the object. One only accounts for gravity, so the net force is just equal to gravity, and the other accounts for both gravity and drag, so the net force is equal to the sum of the force of gravity and the drag force. In this example, two objects fall. The purple one represents the falling motion of an object affected by gravity and drag forces, whereas the blue one is just gravity. We see that the blue object falls faster than the purple one because the drag forces on the purple one cause the object to slow down. For this lab, I videotaped a pudding cup falling after being dropped from my lofted bed. I used Tracker to create an observation-based model and to get data about the movement of the object. I then used the program GlowScript to code two different predicted models, one that only accounts for gravity and a second that accounts for both gravity and drag force. This slide shows the result from the Tracker analysis. On the right is a graphical representation of the motion of the object in the y direction with respect to time. The position is negative because I declared that the up direction is positive. On the left is all of the measured data, including the initial time, final time, t-step, initial position, and initial velocity that will be used in the GlowScript models. This slide shows the major changes I made in the code to get accurate models. I of course made smaller changes like updating the mass, initial position, t-step, and the while loop condition. For the first model, I only included gravity. I did this by multiplying the mass of the ball by the acceleration due to gravity multiplied by the unit vector for the positive y-axis. I then assigned that value to the net force and used the momentum principle to update the ball's velocity and position. For the second model, I did pretty much the same changes as the first one, but incorporated drag. I figured out the b value via calculation and experimentation. I then multiplied this value by the velocity squared and added that value to the force of gravity to calculate the net force. This position versus time graph shows all three models so that we can compare them. As the graph shows, the original model that only takes into account gravity does not represent the object's motion well towards the end. This is because it predicts that the object should fall faster than it actually did. This means that there had to have been another force acting against the motion of the object, which was drag. The model that accounts for drag predicts motion much closer to the actual observed motion. It is still not perfect due to a couple of errors like movement in the x direction, other forces in the room, camera quality, and lighting. To fix these, in the future, I would use something more steady to drop the object, and I would also do it in a room with better lighting so that it was easier to do the tracker analysis. An object hits terminal velocity when it is no longer experiencing any acceleration due to gravity. This would mean that the drag force and the force of gravity are equal to each other, because F net equals 0, which is equal to the force of gravity plus the force of drag. Given this reasoning, it is obvious that two of the three models, the observed motion and the model with both drag and gravity, predict terminal velocity because they account for drag. If an object were thrown down with a non-zero velocity, then the terminal velocity would still be exactly the same. For the thrown object, the drag force would be larger, but it would also hit terminal velocity faster. As shown by the graph, at the end of motion, they both have nearly the same velocity. In conclusion, we use Newton's second law, gravity, and drag force to accurately explain and predict the motion of a falling object.